is I'll start by giving you the general principles dealing with local versus global. We've been through this before. It's just kind of a recap. And then spend some time on a specific case of local spatial autocorrelation statistic, namely the local Moran xi, and very briefly also discuss another alternative, the GI statistic, developed by Art Geddes and Keith Orr. They're very similar, but they're not quite the same, and it's important that you know that their interpretation is different in the sense of indicating clusters and outliers and what exactly these clusters are. So that's what we're going to do today. In terms of the basic concepts or principles, we've been through this several times. Major difference between global analysis, which is concerned with the overall pattern, with clustering, as we've said, which uses one statistic, one number to summarize the whole pattern, such as, for example, a Moran xi statistic. It's one number, and it tells you whether or not the pattern is more systematic spatially than it would be, say, under spatial randomness. Similarly, our K function and our semi-variogram are global statistics. They're characteristics of the overall pattern. The underlying notion is that there is homogeneity, there is equilibrium, there is stationarity, as we've talked about several times. An alternative perspective, and one that has actually gained quite a bit of attention more recently, is, especially with larger data sets, is to realize that this focus on homogeneity is actually quite unrealistic. And instead is to allow heterogeneity, so changing parameters, changing functional forms, maybe changing weights, those kinds of things are not necessarily constant throughout the data set. And then it's important to identify specific locations of interest. So rather than focusing on the overall pattern in a global way, we focus on specific locations that are somehow interesting or different in the sense that they form local clusters or they form local spatial outliers. We saw examples of this in the point pattern analysis when we used scan statistics. We didn't really look at this in the geostatistical analysis, but there's a similar way to focus. Well, in some sense, we did when we allowed directional effects. When we allowed directional effects, we allowed heterogeneity. One model for one direction, another model for another direction. So that's a form of heterogeneity. Here, it's much more specific to each location, and sometimes these tests are also referred to as focus tests because they focus on specific locations. But you have to be careful with this terminology because in point pattern analysis, focus tests pertain to clustering around a particular point of interest. For example, the incinerator in the example of the larynx cancer that we saw earlier on, the Lancashire data set. Okay, so global is one number, local is many numbers. The definition of a local indicator of spatial autocorrelation, or spatial association if you wish, is really two aspects. And we'll see later that some statistics, like the GI statistic, deal with one of these aspects, but not necessarily the other one. And the one is really the important one, the way to characterize individual locations in terms of the presence of spatial autocorrelation, or more precisely, in terms of the absence of spatial randomness focused on a particular location. So that is a local statistic. Very important. It's for each location. So you have as many statistics as you have observations, as many statistics as you have locations. That's going to create some problems with statistical testing, problems of multiple comparisons that we'll talk about later. Because your p-value, your significance value, will be affected when you use the data more than once for a statistical test. That is referred to as data mining before data mining became a good thing. data mining was a bad thing in the sense of, you know, overusing the data and not properly quantifying the uncertainty associated with the data. You all know that if you test long enough, eventually it's going to be significant, and that's the same problem, is the problem of multiple comparisons. The second aspect is a little more subtle, and it's more interesting or more relevant in terms of model diagnostics, and that there is a connection between a global statistic and its local counterpart. And this connection is additive. So the sum of the local statistics is proportional to a global statistic. Sometimes it's equal to the global statistic. In most cases, it's simply proportional to the global statistic. So then you can see how the global statistic is made up. In some, if you wish, you can take it apart into its components. And that's where the diagnostic aspect comes in, where you can identify if there are specific locations or subsets of locations that drive the global statistic. We talked a little bit about this in a different context when we discussed the Moran scatter plot. The Moran scatter plot is, you have a linear fit through a scatter plot to the cloud of points, and the slope of that line is the global Moran psi. Now, you all know that when you do regression, there are some data points that can have high leverage on the slope that you estimate, and that if you take those points out, your slope changes a lot. Similarly, you can think of the global statistic as consisting of all these individual local statistics, and some of these may have high leverage on the global statistic. And that if you would take them out of the data set, you get a different result. Now, why is this important? It's important because of our assumption of stationarity. Remember, everything relies on this equilibrium in a cross-sectional situation. So if you don't have that equilibrium, if you have, if you wish, data points that don't play along, that are very different, then you should be aware of that. And so in that sense, looking at how the global statistic is composed of these local statistics is an important diagnostic, an important exercise to do in terms of assessing the extent to which this broad sweeping assumption of stationarity actually holds. Mathematically then, it is actually a very simple thing, in that every global statistic that can be written as a sum of location-specific components, possibly scaled, so you have a sum over I, where I is the individual location, of individual components associated with I. So there's no J in here. Okay? If you have this connection between these individual components and the global, then the local one is the component. So that's kind of flipping around what I just said, is that we want the connection between the locals and the globals, or you can make it, look at it from the reverse perspective and say, if your global is really a sum over the observations of these local components, then we'll call each local component a local statistic. And so then you can see that there are lots and lots of different types of local statistics. Because one characteristic of many spatial autocorrelation tests, starting with this general local gamma, general cross-product statistic, is that they are double sums. The sum over I of a sum over j of these elements. So for each location I, you can compute the second part. So essentially what this is, as we know, is an average of the neighboring values, right? Where the averaging happens through the weights matrix, the Wij, and the similarity notion is encompassed in the Aij. So for example, for Moran's I, this is a cross product. For Geary C, it's a square difference, right? But for each location, we can compute this. We don't need anything else to do that. And then if we add them all up, we get the global gamma statistic. So in each location I, we compute the average of the neighbors, if you wish, using Aij as the measure of similarity. For each of these i's, we have a value, we add them all up. By construction, there's no magic here. This is just how it's done. By construction, the sum of all of these over the individual locations I is the global gamma. So then we simply call the local statistic gamma sub I, one for each location, which is the sum, the weighted sum, or the average, if you wish, of the neighboring locations using a specific attribute similarity measure. And then we have our connection between the global and the local. This is the same, these two are the same. We have each individual gamma I adding up and totaling the global gamma statistic. So this is the most straightforward case. This is the case where there's simple additivity, there's no rescaling needed at all. We just compute this statistic for each location, add them up, and then have the global statistic. Now the question is going to be, it's all fine to compute a number for each location. How can we assess whether or not this is significant? And we'll get to that in a few minutes. So this is purely, I mean, it's not even algebra really, it's just adding up. Right? There's nothing magic to it. The trick will be, well, can we, assuming that we compute this, can we do something meaningful with it? Can we assess whether this is a value, the value that we observe is large or small relative to what it would be randomly? That is really what we're interested in. So that's going to be our main focus of attention. Since we know that the gamma statistic, the general cross-product statistic, is really a very general class, a broad class of spatial autocorrelation statistics, we can just change the Aij, and we get a different statistic. And so for each of these different Aijs, we get a different local counterpart to the global counterpart. So say we have Moran's I. For Moran's I, Aij is the product, the cross product. Then we'll see later that a local Moran's I is some scaling factor, and we'll specify that scaling factor later, times the average of the neighboring values. Now think back, what are the points in the Moran scatter plot? They are the original observations against the average of the neighboring locations. So this is, if you wish, this local Moran, apart from its scaling factor, is exactly what we used on the y-axis of the Moran scatter plot. That's actually how I got to it. All of a sudden I realized this is what's going on, and then since it's so simple, it was easy to generalize to any other statistic that was additive like this, and since most of them are, it's actually a general class of local statistics, which is pretty kind of neat result. The local Geary isn't used very much, but it's simple to establish. Replace Aij by the square difference, and then we have that. Now, notice the difference between the local Geary and the local Moran. In the local Moran, y of I is in this m part. In the local Geary, y of I is in the statistic itself, which is a little more complicated. And then this other statistic due to Sokol uses absolute differences. Again, the y of I is in here, and it isn't in the local Moran. As we'll see later, it really isn't in the Geddes-Orr GI statistic either, which makes those two, the GI statistics and the local Moran, easier to compute and calculate inference. That's why the local Moran is in GeoDa. Okay, let's focus a little more on the local Moran and some of its, what this M is. And the important thing about the M, and that's why I wrote it that way in the previous slide, is that there's no index there. Meaning it doesn't change with location. It's the same no matter where you are. It's not M of I, it's M. So for individual statistics, for location-specific statistics, you can ignore this part, because this part is the same for each location. Of course, if you want to have the actual value that is meaningful in the sense of connecting back to the global Moran, say your global Moran is 0.5, and you have your 50 local Morans, you want them to add up to something that scales back to 0.5. So then, of course, you need to use this first part. But you don't if you're just interested in inference, because this is the only part that you have to worry about. The M2 does not vary with I. The link is simply a scaling by the number of observations. So if you think about this, you can move this over here, and then you see that for Moran's I, the global statistic is the mean or the average of the local statistics. So there's a very nice connection between the local and the global. So then you can do the kind of analysis that we've done early on when we did the exploratory exploration of the data, and we can see how the mean stacks up relative to the median, for example. Because the mean is sensitive to outliers, the median is much less sensitive to the outliers. So your Moran's I, which if you think of it as an average of local Morans, could be pulled up by some high local value, whereas the median, for example, would not be pulled up and would be lower. And this, again, is an indication of potential non-stationarity in your data, something you have to worry about because everything depends on the same process working throughout the data set. So that's all it is. For each observation, you have the Z of I. You compute, these are the pieces that you have from the Moran scatter plot. You just scale them a little bit, and you have your local Moran statistic, and you're done. Then the question is, how do you know if it's significant, and how do you interpret it? As for the global Moran's I, we have two major approaches, and then within the analytical one and the computational one, and then within the analytical one, we have a number of different ways to proceed. If you remember, for the global Moran's I, we could assume normality and proceed that way. Then our null hypothesis is an uncorrelated, random, multivariate, random variable. Or we could assume equal probability, which we call the randomization, or we could get the exact inference. That was the other option for the global Moran's I. In principle, you could do the same here. The problem is that these analytical derivations for the local Moran I are very bad in that they don't approximate the true small sample properties very well. And you can think of it in the following sense. For global Moran I, the approximation works as the data set grows in size, asymptotically becomes bigger. For the local statistics, it has to grow asymptotically locally in some sense. I know this is a little bit abstract, but you have the same issue say in semi-parametric or non-parametric estimation or local regression. When does local regression work? If your data set gets, conceptually at least, denser and denser locally. But if it doesn't do that, then getting a larger data set is no good because you don't gain locally. You gain globally, which is a different story, but you don't necessarily gain locally. So that's something to keep in mind, and in my original paper I did the derivations, but it's been a while, 10 years more. I've seen so many results and it's really bad, so I don't use it at all. I know some of the software out there does produce the analytical results, but they are very unreliable. And some of the issues that we get on our mailing list is, I did the local Moran in this software, and then I do it in GeoDa, and it's different. Well, it really shouldn't be different. It's because that other software uses analytical approximations which are actually very poor. So if you do the computational, you go the computational route, it's much more robust, but also much less general, because essentially you're just using the data themselves to get this inference. So you don't get actual significance levels or p-values, if you wish. You get these pseudo-significant levels, which are simply a ratio compared to your reference distribution. Now, there's a little difference here, which is important relative to the global Moran. In the global Moran, we reshuffle all the data and then we compute the statistic. For the local Moran, we can't do that because it's location specific. So we have to hold the value fixed at the location that we are considering. Let's say we have 50, let's say North Carolina, 100 counties. We pick one county. The value that we observe at that county, we take it and we fix it at that county. And then the 99 other counties, they get reshuffled. And we do this the same 99 times or 999 times. And for each of these reshufflings, we recompute a local statistic for that particular county under consideration. Then we move to a different county. Again, fix the value at that county and reshuffle the 99 other ones. This is called conditional permutation. It's conditional because you're not shuffling everything around. You're shuffling everything except the location that you're focusing on. Now, think computationally. What this means is that you have to repeat this reshuffling, whatever, 999 times for each location. So say if you do 3,000 counties of the US, and let's say you do 1,000 permutations, that's 3 million calculations. That's a lot. But it's simple because the local statistic only needs the immediate neighbors. So whereas for the global statistic you have to compute all of them, for the local statistic you just have to look at the immediate neighbors. So your weights matrix tells you which ones these are. Say you have 5 neighbors, then you only need to work with 5 of these resampled values. So you don't just need to draw 5 out of the pot of 99, say in the North Carolina example, and recompute the statistic. You don't have to generate all of them because the ones beyond the immediate neighbors, they never really come into play in the statistic to begin with. So it's not as complicated as it sounds, but it's still complicated. So this is the preferred way to do it. So then for each location, you get an assessment of the extent to which the particular value computed for that location is compatible with spatial randomness. Okay. For each location in turn. And that's where the trouble starts. Because what is this p-value really worth? Now, if you do this for 3,000 counties, you have carried out 3,000 tests with the same data set. Is it the same data set? Well, not totally, but somewhat. There's an overlap between the neighbors. So there is at least some commonality in terms of the neighbors between locations as you move from one to the next. So they do reuse the data, but it's not as bad as reusing the data, all of it, all the 3,000 observations. And that's the problem, because we have some very nice rules to deal with multiple comparisons, but they don't really work in this case because we don't really know how much multiple comparisons we do. And there are there's some interesting work being done in that respect. Comes out of psychology. I should have looked it up, but there's an acronym for it. But it's basically trying to, what is it, false rejection rate, something like that. Anybody familiar with that? There's some recent literature. I can give you a reference, but it is the classic method is a Bonferroni bound. Anybody heard of that? So if you do, say, 5 tests, and your target p-value is 0.05, then for each of these tests, you should use 0.05 divided by the number of tests. So that would be 0.01. So if we do 3,000 tests, and our target value is 0.05, then using the Bonferroni rule, our p-value should be 0.05 divided by 3,000, which means basically we'll never get anything that is significant. So this, and forget about 100,000 data points. So that doesn't really work. So I'll talk about that some more later, but it's something to keep in mind when you interpret the results, in that the p-values that are given, say, by a GeoDa, are not really correct. They're not correct because they don't take into account the multiple comparison aspect. How to correct them is a different story, and that's actually very tricky. So my approach to this is to do sensitivity analysis and to see how the results change if I change the p-values and if I change the number of permutations. So the way we visualize this is in what I call a Lisa significance map, which, and it's very important to realize what's going on here. Only those locations with a significant local statistic are shown on the map. And there is a tendency, and it does happen in some software packages, that all the local Morans are mapped because you have one for each location. However, if they're not significant, there is no point in mapping them. Because if they're not significant, then that location, if you wish, in some sense, is locally spatial random. And there is absolutely no point in creating a false impression that something is going on there when in fact nothing is going on there. So ideally, this map should be a 0-1 map. You're either significant or you're not. Now you can, and GeoDa does this, show different gradations of significance. So for different p-values, you get a slightly different shape. But the importance is you're in or you're not in. Okay. And so don't make a map of all the local Moran on, because 90% or more of those values are misleading because they are not significant. You shouldn't even look at them. There is nothing going on with those locations of any interest to you. So let me just point it out again. And I say this because there is software out there used by many people that does this. Okay? This is no good. You should not show locations that are not significant. It's the same as when you do regression and a coefficient is not significantly different from 0, and you say something about its sign. You should never do that. 0 is 0. 0 doesn't have a sign. So when you cannot reject a null that it's different from 0, then it is 0. Then there's no point discussing the sign or anything like that. Same here. If you cannot reject a null that it's spatially random, then it is spatially random and of no interest to you whatsoever in terms of clusters or outliers. So that is the principle behind this Lisa significance map. Then, so this is what it looks like. This happens to be North Carolina. And you have different shadings. It's a little harder to see on the screen than on my monitor. But you get the main idea. These are a little darker than the other ones. Now, what have we said about this p-value? Because it's based on randomization, or permutation, the actual p-value is a function of how many permutations you do. So for these local statistics, for the global Moran's eye, I think we've said in the lab and in the lecture, usually 99 is good enough. It gives you a good idea of whether something is going on or not. For the local statistics, that is not the case. For the local statistics, I actually recommend running 10,000, so 9,999. And you will see changes. So this is very disconcerting the first time if you don't realize what's going on, in that if you rerun the analysis, you get a different set of permutations, and some of these quote-unquote significant locations drop out, and some others come in. These are typically the ones at the bubble. The ones on the bubble at the P05 level. So it's a good idea in practice to, you can look at this quick and dirty, but if you really want to draw some conclusions from this, you should run it with 10,000, run it a couple of times, and then you will see the marginal ones popping out or popping in. And those are the ones you should consider with great caution. Typically, there is a core that is very significant and remains very significant. But then there's others on the bubble, which really is where the multiple comparison comes in. Because if you go really at 0.05 in this kind of analysis, it isn't 0.05. It's probably more like 0.20, and that's not really significant. But if you get them to be 0.0001, then you can do a lot of comparisons before you get in trouble. So that's my rule of thumb. It's nothing very precise, but it is be very cautious not to draw too many conclusions from P05. That is probably not a meaningful finding. The other, and then in many ways the more meaningful visualization of the local Moran is what we call a Lisa cluster map. Again, only the significant locations. So in that sense, it matches the significance map in that you only see color where something is significant. But what we're doing in this one is we're tying this back to the Moran scatter plot and its categorization of spatial autocorrelation into 4 types, each of these corresponding to a quadrant in the Moran scatter plot. So we had positive spatial autocorrelation, the high-high and the low-low, and we had negative spatial autocorrelation, the high-low and the low-high. So now we can do this for each individual location. For each individual location, we compute the local Moran, we assess whether it's significant or not, and then from its sign and its magnitude, we can conclude whether this is a high-high, low-low or high-low, low-high situation. Because we know where it is in the Moran scatter. And so putting these two together gives us this map, which in GeoDa uses red for high and blue for low. And here we see I picked this one because it has all 4. In practice, you often do not have all 4. There is no requirement to have all 4. Okay? You could very well have a map with just 2 types, or even just 1 type. There's no requirement because you remember in the Moran scatter plot, there's no significance. All of them are in there. Okay? Here, only those points from the Moran scatter plot that in fact have significant local statistics are being shown. And so what you could do in GeoDa, for example, is click on one of these that is significant and then see where it is in the Moran scatter plot. And we've kind of short-circuited that process by giving a different color code. So what we see here, these dark red ones are clusters, and I'll get to that in a second, of high values surrounded by other high values. Now, always high is relative to the mean. We have everything centered to the mean. So that does not imply that these are necessarily very high values. They're just, it's in a relative sense. They're above average. Above average surrounded by above average. Below average surrounded by below average. And then those are clusters. Clusters of high values, clusters of low values. And then we have the spatial outliers, which are the reverse. The light blue ones are low values surrounded by high values. Now, high again relative to the mean. And compared to what this would be under spatial randomness. So, under spatial randomness, how likely is it that we get this low value surrounded by higher values? Is that likelihood is small enough, then we say it's significant. And then we call this a spatial outlier. It is different from its neighbors. Significant in the sense of the word that we've used here. Significantly different from the neighbors. And then the reverse, obviously, is these here, where you have a high one surrounded by low. In some cases, these outliers are actually very different. Very interesting. They point to locations that are very different from their neighbors, so they point to possible problems with, again, this notion of stationarity. They also may indicate zones of transition, where you go from, say, a stratification with high values on one side, switching to low values on the other side, then the zone of transition can be spatial outliers if it's different enough. The clusters themselves are, I think this is, I'll talk about that after the break, but think about it. You know, a cluster is a location similar to its neighbors, but we only show the location, we don't show the neighbors. So the cluster is actually bigger than this, and I'll show you this in an example in a few minutes after the